Fast, extremely fast, the fastest thing we know. All right, but why is that the limit? Why is it impossible to go faster? What exactly prevents it? Most people have never really asked this question seriously. They just accept the answer. Einstein said so. The speed of light is the ultimate speed limit of the universe. That's just the way it is. But that isn't an explanation. That's simply repeating a statement without understanding it. When you truly ask why nothing can exceed the speed of light, when you look at what is actually stopping you, you uncover something profoundly strange, something so far removed from everyday experience that it fundamentally alters how you think about space and time. The speed of light is not merely a speed. It isn't just the fastest thing that exists. It is part of the underlying structure of the universe itself. It is woven into the fabric of space-time in such a way that going faster is not merely forbidden, it becomes physically meaningless. Let me show you what this means. Let's begin with something simple, something familiar to everyone. Things fall. Drop an object and it falls downward. Galileo measured this precisely, about 16 feet in the first second. Drop a ball, drop a rock, drop anything. In 1 second, it falls 16 feet. Now consider the moon. The moon moves around the Earth. It doesn't fall straight down. It stays up there, orbiting, moving in a curved path. But wait, is it falling? Think about it carefully. If the moon were simply sitting still in space, not moving sideways at all, what would happen? It would fall straight toward the Earth. Gravity would pull it inward. The moon remains in orbit because it is moving sideways, tangent to its path. Gravity pulls it downward, but its sideways motion causes it to continually miss the Earth. It falls toward Earth while never reaching it. That is what an orbit really is. Continuous falling combined with sideways motion fast enough to keep missing. This is where Newton had his brilliant insight. The moon is about 240,000 miles from Earth's center. We stand roughly 4,000 miles from that same center. That means the moon is about 60 times farther away than we are. Newton asked a critical question. What if gravity weakens with distance? What if it follows an inverse square law? If you go twice as far away, gravity becomes 4 times weaker. 3 times as far, 9 times weaker. In general, it weakens with the square of the distance. If this is true, then at the moon's distance, 60 times farther, gravity should be 60 squared times weaker, that is, 3,600 times weaker. On Earth, objects fall 16 feet in 1 second. If gravity at the moon is 3,600 times weaker, then the moon should fall toward Earth by 1/16 divided by 3,600. Do the math. 16 feet divided by 3,600 is about 1/12 of an inch per second squared. Let me phrase that more carefully. In 1 second, an object at the moon's distance should fall toward Earth by about 1/12 of an inch multiplied by the square of time. Over the appropriate time scale, that works out to the same 16 feet we measure on Earth. Newton calculated how far the moon should fall in 1 second if gravity followed an inverse square law, and it matched perfectly. This was enormous. This wasn't just a theory. It was a prediction. Newton connected one completely independent fact, how fast things fall on Earth, with another completely independent fact, the moon's orbit and distance. 2 unrelated observations became linked by a single law, gravitation. There was no going back. Newton went further. He calculated what shape planetary orbits must have if gravity follows an inverse square law. The answer was an ellipse, and that is exactly what planets do. Kepler had already measured elliptical orbits, but he didn't know why. Newton explained them. One law accounted for multiple phenomena at once.
Then more pieces fell into place. The tides. Why do tides exist? Because the moon pulls on the Earth. But if the moon simply pulled Earth toward it, there should only be one high tide per day, the bulge of water on the side facing the moon. But there are two tides per day, roughly every 12 hours. Why? Some thought the Earth was pulled away from the water. Others thought the water was pulled toward the moon. Both ideas were partially correct, but neither fully explained it. Newton saw what was really happening. The moon's gravitational pull on the Earth and on the water is nearly the same at the same distance, but the water on the near side is slightly closer to the moon, so it is pulled more strongly. The water on the far side is farther from the moon than the Earth itself. As a result, one bulge forms where the water is pulled more, and another forms where the water is left behind. Two bulges, two tides. In fact, Earth and Moon both orbit a common center of mass located inside Earth. Centrifugal effects and gravitational differences combine to produce the observed tides. With this, many other things became clear. Why Earth is round, why it bulges at the equator, why the sun and moon are spherical. As science advanced and measurements became more precise, Newton's law faced increasingly strict tests. One of the first involved the moons of Jupiter. Careful observations showed that their motions sometimes appeared about 8 minutes ahead of schedule and sometimes about 8 minutes behind schedule relative to Newton's predictions. 8 minutes is a huge discrepancy. Something seemed wrong. But then an important pattern emerged. The moons appeared ahead of schedule when Jupiter was closer to Earth, and behind schedule when Jupiter was farther away. Ole Romer, trusting Newton's law of gravitation, reached a bold conclusion. Light takes time to travel. What we see is not how the moons are now, but how they were when the light left them. When Jupiter is closer, the light arrives sooner. When it is farther away, the light arrives later. By correcting for this delay, Romer was able to determine the speed of light. This was the first demonstration that light does not propagate instantaneously. Notice what just happened.
The speed of light was discovered not by measuring light directly, but by trusting a different law enough to notice when something else didn't fit. This illustrates something profound. When a law is correct, it can be used to discover others. If something doesn't match, it may point to a new phenomenon rather than an error. This process has continued for centuries, an avalanche of discovery, each insight enabling the next. Now comes the truly strange part. Once the speed of light was measured, something astonishing became clear. Light always travels at the same speed. Always. No matter who measures it, no matter how fast the observer is moving. Stand still and shine a flashlight. You measure the speed of light as 299,792,458 meters per second. Now get on a train moving at half the speed of light. Shine the flashlight forward. Common sense says the light should move faster, but it doesn't. You still measure 299,792,458 meters per second. Increase the train speed to 90% of the speed of light. Same result. 99.99999% of the speed of light. Still the same number. The speed does not add. This contradicts everyday experience. Normally, speeds combine, but light does not behave that way. Einstein realized the implication. Space and time are not fixed, they are flexible. They stretch and compress to keep the speed of light constant. As you move faster, time slows down for you. Your clock literally ticks more slowly. Distances along your direction of motion contract. These are real effects, they are not illusions. As you approach the speed of light, your inertia increases.
It becomes harder and harder to accelerate. To reach light speed would require infinite energy. Nothing with mass can reach it. Photons can, because they have no mass. They must travel at that speed. Why is the universe built this way? There is no deeper why. The speed of light is not imposed on the universe. It is a consequence of the geometry of spacetime itself. Spacetime has a built-in conversion factor between space and time. That factor is the speed of light. You are always moving through spacetime at a constant total rate. If you move faster through space, you must move slower through time. At the speed of light, time stops. This has been tested repeatedly. Particle accelerators, GPS satellites, cosmic ray muons all confirm it. The speed of light is the maximum rate at which cause and effect can propagate. It is the speed at which information travels, the speed at which reality updates itself. And this entire chain of understanding began with watching the moon fall sideways. That is the avalanche of science, still moving forward. The speed of light is not just a number. It is the key to how the universe works.